Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, we are going to look at all sorts of different types of wood connections that are available on the market, including nails, bolts, other types of shear plate connectors, truss plates, timber rivets, glued-in rod, self-tapping screws, basically the whole gamut. And in this course, we're going to focus on the technical design of nails and bolts, but a lot of the concepts that we'll be covering in terms of those two connection types will also transfer to all those, or at least a lot of those other connection types. Okay, so there's a lot of things that we might want to consider when we are designing connections in wood. And the thing about wood connections is they often end up being the weakest component of the timber structure, because a lot of the ways that we connect wood engage some of the brittle failure mechanisms that we talked about when we talked about wood strength and mechanics in general. So in order to design timber connections that have really high strengths, that can be a challenge, and we'll see in this lecture some of the options for designing connections that have larger strengths than maybe conventional connections do. In fact, for heavy timber connections like ones that you see here, sometimes the entire strength of the member is often governed by the connection instead of the strength of the member itself. There are a lot of things that we would want to consider, of course, when we're talking about wood connections. Cost is probably one of the most important, if not the most important, in a lot of cases, but also aesthetics are very important. You can see in this figure here, these are kind of concealed types of connections where plates are slotted into wood members, so you don't really see the big steel plates that are connecting these together. So there's a lot of ways that we can do concealed connections like that. See, fire is a big consideration. We're not going to talk about that explicitly here, maybe in a shorter lecture in the future. But one thing that it might be interesting to know at this point is that actually having exposed steel in the connections can be actually something that governs for fire design. So that's another benefit often of using these concealed connections, because believe it or not, heavy timber is pretty good in wood because it takes quite a long time to burn through a very big, thick timber member. So sometimes concealing the steel plates, like shown here, actually gives a benefit for fire design as well. Durability and acoustics, we're not going to cover a lot here, but of course strength, stiffness, and ductility are things that we're always interested in. And when we look at designing these timber connections using the clauses in the standard, these are going to be our primary considerations. But of course, ease of fabrication is one that is maybe kind of a hidden consideration that as you get more experience doing wood designs, and maybe having those designs actually come into reality and seeing what happens when these members get fit up in practice, you probably get more experience in designing things that are easy to construct. Of course, bolted connections like this are some of the things that are the easiest to construct. But even with some of the other maybe more some of the kind of connections that have come online in the last 10-20 years are ones where ease of fabrication and ease of construction are maybe the primary benefit. Okay, so another trend that has happened in the last maybe last 10-20 years is really the advent of computer controlled machining for timber members, which allows you to make very precise cuts and routings and holes that make them just as easy to fit up as maybe equivalent structural steel members are. And this is kind of a revolution in a sense for timber construction, because if I can use these heavy timber glulam or CLT and do all of the holes and slots and fit ups and everything in the shop before I send them to site, then you get a really huge fabrication and construction advantage in terms of time. So it's basically just coming with pieces that we know already easily fit together, bringing them to site, and just kind of bolting them all together. and not having to worry too much about the tolerances, because with, you know, machines like this, we can get, you know, probably sub 1 millimeter tolerance or something like that. So very high precision. Okay, so basically I'm going to go through and talk about all the different types of connections. We're going to start with nails, and I'm going to talk about bolts and all those different things. So, you know, we're probably already familiar with what a nail is and what a nail looks like. But you also probably know that nails are very easy to install. You know, in the limit, you can do it with a hand tool, a hammer. Often in construction, they'll use a pneumatic tool to do the nail installation. But basically, nails fit up through friction. You insert the nail, and the nail pushes aside the wood fibers. The idea is the nail is going to push aside the wood fibers when I nail the nail in, and the friction is what keeps that nail in place, of course. And so sometimes the profile of the nail will include depending on what kind of nail you're using, might have a texture that helps with that friction. But the primary way that we load nails is not a pull out like this, but instead shear connections like this, where I have something pulling on the member and the nail is held in place by friction for vertical lateral loads. Yeah, so nails come in diameters, you know, up to around 4 millimeters. There's nails and spikes. Spikes are just nails that are basically bigger. You can get about 0.5 kilonewton to 2 kilonewtons, something on that range of design load per nail. And so that gives you an idea. Usually for any kind of sizable connection, you're going to use a lot of nails, and you're going to space them out. But that turns out to be a very good way to do wood connections, spacing out all of the connection elements, which we'll talk about a bit more in a future video. So this is from the Introduction to Wood Design book. They have some pictures of nails and what kind of lengths they are. In the design manual, in the standard, there are actual selection tables for nails, which we'll look at when we talk about the details of how to do nailed connection designs. But you see we have different shanks, different heads. Spike is the one on the top, regular nail is the one on the bottom, and you can see the difference is just basically in the size. Okay, so the most common place where you're going to see nails like this is in residential construction. Light frame construction is typically done entirely with nails, mostly with nails, with probably a few bolts for hold downs and stuff like that. But you know, this is a very common way to go about doing light frame construction. But nails can also be used for heavy timber construction. This one is a little bit heavier. You can see the nails just right here. Bring up my pointer. Yeah, so you can see some nails right here that are holding this this kind of purlin or something to this larger beam. And if we have something that, as we mentioned before, if we have quite a lot of force that we need to resist, for example, in this case of this pretty heavy duty hold down that's at the outside of a light frame shear wall, we can just use a lot of nails and lay them out in a matrix pattern. And this is an easy way to connect a steel plate to a timber member, as long as we're loading it in shear like this. Again, we can't use nails to do loads that are pull-out loads, because they don't have significant resistance to being pulled out of a member. You can do it with hand tool very easily. Okay, when we connect joists to beams and stuff like that, often we're going to use joist hangers, which we have seen before. These are just members that connect between a joist, and this one in the back is a larger timber member, and those are almost always also connected with nails, usually using a powered nail gun to make installation a little bit easier. Another interesting thing is here, this is a wood eye joist, and you can see that, you remember that for joists and beams we're required to provide rotational restraint at the support, top and bottom. Like, we're supposed to provide lateral strength top and bottom at the end of a beam, right? That was one of our requirements when we did beam design. And you can see the way that this joist hanger works. Obviously, it can't come inside the flange to connect to the web. So actually, you're required to provide a blocking here so that we can have the joist hanger connect to the blocking. And now this blocking with the hanger together prevents the twist that would be possible otherwise with this I-joist. Okay, so the next common thing that you might think for construction would be wood screws, because probably if you ever done anything around your house or anything like that, you know, you might have often used wood screws to put things together. But wood screws are not terribly common for structural design unless you need something that has a good withdrawal resistance, something that you can actually load and pull out, because they tend to be less ductile than nails. And so nails can bend and bend and dissipate energy through inelastic bending over and over and take quite a few cycles back and forth. Whereas the way that screws are manufactured makes them kind of considerably less, typically less ductile. And so we don't usually use screws, for example, to make light frame shear walls. Okay, although you might think it's a good idea because, you know, you'd say, well, a screw's going to hold in better than a nail, so we should probably use a screw. But one of the primary things that we need to do is in the shear behavior, the sheathing connected to the studs, they need to move kind of laterally to each other when the wall deforms. And screws are not so good for that because they don't have that kind of inelastic capacity in that kind of shear movement. But they are very good if you need something that needs to have a withdrawal strength. It also takes a longer time to install them than nails, right? So if I have nails with a pneumatic gun, then they're very easy to install. Screws take a bit longer because you have to wait for it to screw in, obviously. You know, it might not be very long on the scale of one or the other if we're just doing one, but, you know, over the time of installing hundreds or thousands of these, it's going to lead to a significant difference. About the same strength as screws. You don't need to pre-drill usually for screws like this. But as I said, the difference is that screws can tend to be pretty brittle, so they don't have as much inelastic bending capacity. Okay, so the next one that we're going to talk about in this course, and we're going to learn all about designing these kind of connections, is for bolts and dowels. Like I have a little bolt right here. And so bolts are a really common way to make wood connections. We've seen a lot of pictures of wood connections that use bolts, either connecting wood members to other members with bolts or connecting wood members to steel plates with bolts. You might see them in diameters, you know, for wood applications. Usually you're going to be using something on the order of a 1/2 inch or 3/4 inch. You could potentially see up to 1 inch for really big members. Like that would be a pretty large bolt to use. That's kind of the larger bolt that you use for steel design, right? Is a 1 inch diameter bolt. Could be up to 1.5 inches, but that would not be very common. I mean, for smaller timber connections, a 1/2 inch bolt that looks something like this is probably a common type of bolt that you would see. So each bolt can transfer quite a bit more lateral strength than a single nail, right? You can get up to, you know, maybe 30 kilonewtons per bolt, something like that. But unlike nails I can just kind of drive in and fit it in between the fibers like that. For bolts, we are going to have to cut a hole first. We can't just obviously push a bolt through a piece of wood. It's too big, can't fit between the fibers. So we're going to have to pre-drill for bolts. That pre-drill hole is going to be a little bit bigger than the bolt typically, if we're talking about bolts. And that helps with fit up, obviously. But, you know, in traditional heavy timber construction, bolt is the way. You know, now these days we're going to talk about a lot of different options for heavy timber construction that don't use bolts, but bolts are kind of the classic and, you know, still very much popular and in use. In terms of ductility, bolts can provide some ductility, but it really depends on the size of the bolt. And when we talk about bolt design, we're going to talk about all the different ways that bolted timber connections can fail. A ductile way is one of them, and that is a desirable failure mechanism, basically where the bolt bends inelastically, it bends permanently. and that dissipates some energy. And that is a ductile type of failure mechanism, but it really depends on my geometry of the bolt and the geometry of the members, whether I'm going to get a ductile failure mode or not. So often with bolts, we generally, with larger bolts, we're going to be likely to get some kind of brittle failure mechanism in our connection, which means a failure mechanism basically that's going to generate some kind of cracking in the wood and basically instantaneous failure after the cracking. So those are pictures of bolts by themselves. This is a picture of some kind of bolted connections, but these use dowels instead of bolts. And the only difference between a dowel and a bolt, I mean, they work the same way. The design is the same. All the design equations are the same for dowels and bolts. But the difference is for bolts, I'm going to cut a hole that's bigger than the bolt, and then I'm going to fit up the bolt inside. The bolt is then going to be held in place using a nut, right? Like I've got my nut here. Those are the washers. I've got my nut here. My nut is going to thread on the bolt, and that's what's going to hold the connection together. Okay, in the case of dowels, for a dowel, I basically cut my hole the same size as the dowel. The dowel does not have a head. It does not have a nut. The hole is cut like basically just a little bit smaller so that it fits in with friction. So in order to install a dowel, I'm going to have to use a hammer or something to force the dowel into the hole. And since the dowel and the hole, like maybe the hole is just a little bit smaller than the dowel, they're about the same size, the friction fit between the two is going to keep that dowel in place. But from the point of view of design, it's basically the same. So we design dowels the same way that we're going to design bolts. Dowel is just basically a steel rod. Okay, so there's all sorts of different ways that I can do bolted connections. I have a bunch of examples, and this is the way that we refer to them. Actually, we'll refer to wood-steel connection, steel-wood-steel connection, wood-wood-wood connection. Basically, what we're talking about is just the order that the members are connected. So this connection over here, if you're from Ottawa, you probably recognize what particular store this might be. If we look here, what we have is 3 members connected together, 1, 2, 3. And so that would be a wood-wood-wood connection. And these long bolts go all the way through all 3 members. So that's a wood-wood-wood connection. You can see that we have kind of a bit of a problem with this connection to do with shrinkage. You can see these cracks. We have a crack at the center of this member. We have a crack at the center of this member. And this is due to differential shrinkage. So remember that timber wood shrinks much more in the perpendicular to grain direction than it does in the parallel to grain direction, right? So let's assume for now that, it's more than an order of magnitude less in the parallel to grain direction, right? So let's say that the parallel to grain direction was 0 for the sake of argument. Let's say it didn't shrink, and only this dimension shrinks across the perpendicular to grain direction, because that one is much, much more. Okay, so let's say that I have these 2 wood members connected together. And this is a problem also in steel connections. Okay, I have these 2 wood members connected together, and this one in the back does not want to shrink in this direction. Okay, so along this entire length, it doesn't shrink. Not very much, very small amount, because it's longitudinal to grain shrinkage. But this member does want to shrink. If I put 2 bolts here connecting these 2 members, this wood member wants to shrink if it gets dry, and it wants to expand if it gets wet, right? So moisture content is going to cause this to shrink and expand. Now the one behind, which the bolts also go through, does not want to shrink and expand in that direction, right? So the one at the bolt is going to hold the one at the back is going to hold those bolts in place, while the one in the front is going to try to shrink. And so as the one in the front tries to shrink, we're going to get a tension stress in between the 2 bolts, and that tension stress is going to create a crack in the middle, if those 2 are too far apart, for example. Okay, the bolt holes themselves can accommodate a little bit of that, but only up to a certain point, right? So here, these are pretty big members. We have 2 bolts like this, and so as the front member wants to shrink in this direction, the back member does not allow the bolts to move in that direction, which means the bolts stay in place and the member shrinks between them, which creates a tension stress, which causes a crack. In the same sense, if I had 2 bolts in this direction, then this member will not allow shrinkage, but the back member will want to shrink, so the back member would also crack. So you can imagine if I have a matrix of 4 holes here with 4 bolts, 1, 2, 3, 4, then I'll get crack in the front member in this direction, and I'll get a crack in the back member in this direction, which is exactly what we see here. So that's just a bit of a example, a real life example of when shrinkage can cause a problem for us. Okay, here's another example of a wood-wood-wood connection. I'm talking about the connection up here or down here. Okay, so here we just have 2. We don't have a big problem in this case. The glulam member is going to shrink probably a bit less than the timber member. The other thing that you will notice here that I want to point out while I have this picture up is this flashing. You see this steel flashing on top, or you know, it might be aluminum flashing. I don't know what it is. With a little lip. It has a little lip on the edge that's very difficult to see. But the point of this is to when water falls on top of this, to shed the water off. Especially important on this front face, because this is the end grain of the member. As we learned about when we talked about moisture in wood, it's much easier for moisture to go into the wood from the end grain, where we have all of the open holes of the straws, than it is for the water to get in on the side grain, which is kind of the side of the fibers, the side of the straws, if we're thinking about wood fibers as straws. So it's important to keep this face dry as much as possible if we want to keep our wood member dry. You'll see we have the same kind of thing over here, where we have a vertical column, and on top it is capped with some steel flashing to keep the top from getting too wet. So if we have wood members outside, it's a good idea to try to keep them dry as much as possible. Here's an example of a wood-steel-wood connection. So here we have a steel plate. There's a steel knife plate in here. We call that a knife plate because it's kind of like, it looks like it's kind of cutting the wood member. So I have my wood member like this, and I cut a slot. I cut a slot here, and I insert my steel plate, you know, into the slot. Wow, this actually does kind of have a slot. So it's like I'm putting the steel plate in the slot like that. That's a knife plate connection. Here we basically would design this as 2 separate wood, steel, wood connections. I'd have the one on the left, wood, steel, wood. Then I have the one on the right, wood, steel, wood. It tells you how to design that in the standard. Yeah, so the nice thing about this connection is it's nice and hidden. So you don't actually see the steel plates, except for this one here that joins them together. So it's a very attractive kind of type of connection. And then you can see that that steel plate is held in using bolts. And in this case, the bolts aren't all installed yet. You can see there's some holes. This is a kind of under construction picture. Here's another example of a wood, steel, wood. So you can see there's kind of a brown steel plate here. You can see an example of some where we haven't had members installed yet. And this wood member has a slot. This big glulam piece has a slot, and the steel plate goes in the slot. And so we're basically using the steel plate as a proxy to connect the different pieces of wood together. This is a really neat, here's another picture from the same building, which has these lovely trees. I think this is maybe in Mississauga. And you can actually see a kind of dowel or drift pin here. So the steel connection here is attached to the side of this with nails, and then the piece that's going to go on here that's not there yet is going to have a slot to accept this piece of steel, and then it's going to be held in place with bolts or dowels. Okay, this is another wood, steel, wood. Here you don't see any steel at all, but you can tell there must be something in between these because these wood members are not slotted into each other. There's no mortise tenon joint or anything like that. So there's a hidden steel plate in here, and these bolts connect the, there's a steel plate that is in all 3 of these at once, and then the bolts hold the steel plate in place. The opposite of the wood, steel, wood connection is the steel, wood, steel connection. So this is basically, we have steel on the outside, the wood members on the inside, and then you'll have an identical steel member on the other side, which you can't see here. But so there's steel, wood, then steel on the other side. It's just basically clamping 2 pieces of wood together with steel plates. and then bolting those steel plates through the bolting those steel plates to the wood using bolts going through all three. This can be very attractive, especially, you see a lot of pictures of the kind of nice wood with kind of black colored steel plates. Makes a nice contrast. It can be very nice. Okay, another application for bolts is hold down connections. So this would be, for example, I'm connecting steel to a piece of wood directly. So that would be like steel wood. Or if I had it like this, it would be steel wood with a bolt in between the two. I think there's a close-up here. But before I get to that close-up, you can see for light frame shear walls, as we talked about before, we need to have hold downs. The hold downs keep the wall from rocking. Because if I have my wall here and I push on the wall, it's going to want to rock up. So I have to hold it down at both opposite corners. And so I can use a bracket, and then the bracket will be connected to the foundation at the bottom. Or in upper levels, you'll see that we connect one bracket on one floor to a identical bracket on the next floor. And it might look something like this. We just saw an example of this where the steel angle was nailed to the cords of the wall, but we could also use bolts instead. So here's an example where I have a steel to wood connection. So that's a steel wood connection. And then of course at the bottom, this is held down either, potentially using a bolt, probably either to the floor below or to the foundation. Okay, so bolts we're going to spend a lot more time on in future lectures. But for now, we're going to go over some of the other things that we're not going to cover in future lectures. So just so you know that they exist. And one of those is lag screws. So lag screws are not like regular wood screws. They're more similar to bolts, except they don't have a nut. Okay, so they're kind of a cross between screws and bolts. The resistance, like the mechanism for resisting lateral load on a connection interface is similar to how it is for bolts. Except these can have a very high withdrawal strength. So it means if I have a lag screw, like if there's a lag screw and not a bolt, and I screw that into the piece of wood, and then I have something that is providing a load like this that wants to pull the lag screw out, it has a very high resistance to that withdrawal force. Usually you don't have to pre-drill to install these, but you might need a lead hole, which means basically you drill like a pilot hole just to make sure that when you put in the screw, it doesn't kind of divert off to the side as you're putting it in. And these have diameters similar to diameters of available bolts. Yeah. So if you only have access to one face and not the other, like if this is something that's really thick and I don't want to go all the way through it, like let's say it's this thick and I want to connect something to the side, but I don't want to have something that goes all the way through, then a good option would be potentially to use a lag screw. I mean, I think also called a lag bolt for that. I have some examples of what that looks like. So here's an example where a lag screw is connecting a steel plate to a timber member. So you can see, you would make a lead hole that would be as long as this, and then you would potentially provide a counterbore because the entire shank you can see is not, you can notice that the entire shank of this does not have a thread. There's some part that does not. This is the part that's supposed to be intercepted at the interface, right? So you can see there's a shear interface here between the steel bolt and the wood. One is going to move relative to the other, obviously, is the whole idea of this connection. So let me show it so that you can see the steel side. The steel is going to want to move relative to this, and that's why I'm putting the bolt here, right? Is to prevent these two from moving relative to the other. But at the point where they are adjacent, like where they're touching each other, that's called the shear plane. And it's much better if I have a bolt here, that I want that shear plane not to go through the threads because the bolt is much weaker at the threads. So if this is where my primary resistance of the bolt is, like this is where the bolt is taking the shear load, the shear between the plate and the timber, then here I want to have, as big of a diameter as possible. So that's why they'll leave some space here that does not have threads, because it's going to be much stronger here without the threads. Yeah, the rest of these are just some definitions that we don't really need to worry about. But anyway, we're going to penetrate that certain distance into the timber member, that lag screw. So here's an example. This is from the Richmond oval that we've seen a picture of the inside before, which has really big curved glulam beams. On the outside, there are these diagonal braces, and these diagonal braces at the end are connected to a big solid steel pin connection. You can see the pin here, using lag bolts, which are threaded through at the end of the member. So basically we're penetrating into the end grain of the member here. So it's nice. It's kind of, it looks pretty hidden. So we couldn't do this with a bolt, obviously, because where would we put the nut, right? So screw is one way to do this. Okay, truss plates are used a lot for light frame construction, and they're called truss plates because they're usually used to put together trusses, like big light frame trusses. So you can see here, I'm going to go back to that one in a minute. You can see here some roof trusses, and the trusses are connected by these truss plates. The advantage of these truss plates is they're super easy to install, because basically what I can do is I can lay out all of my truss members on the ground, like horizontally, lay them all out, put these truss plates on top and on the bottom, so one underneath and one on top, at each intersection point of the diagonal members and the cords of the truss. And then if I have a big press, I can basically press the whole thing together at once and install all of the truss plates. So I just lay it out. I put these truss plates. These truss plates are basically just light gauge steel with some spikes punched out of them. So it's like I start with my steel plate and I punch out a coupon of the plate to make a little spike. And then, obviously I don't do that. I'll buy it off the shelf, and then I can just lay everything out and then just smush it all together and make a prefab truss. And so that's what it might look like in practice. These are pretty heavy ones for, this is a pretty heavy application of truss plate, like maybe a lighter, 2x material is maybe even more common. Okay, this is something else that's in the standard that we're not going to talk about in a lot of detail, but I just want to make you aware, because it does have some good potential applications, is called a split ring. You can see it's a ring of steel, and the split is just that the steel is not connected all the way around. There's a disconnection here. So this split ring can actually open up and close up a bit. And that allows some flexibility on the size of the cavity that I install it in, as we're going to see in a second. So here's what we do. We take a piece of wood, we drill out this groove, and that groove is half in one piece of wood and half in the next piece of wood. So I have a piece of wood, I have a second piece of wood. I'm going to take a groove out of this one, and I'm going to take a groove out of this one as well. That's the size of the split ring. So the split ring is going to sit half in one and half in the other, and then I'm going to put them together. And now that split ring is going to provide a connection between the two that has a very high resistance per split ring, because I'm engaging a much larger area of this piece of wood. Then I have a bolt that goes through the middle, and the idea of that bolt is just to hold the two pieces of wood together. So the shear resistance, the movement between these two pieces of wood, is provided by the ring, and the bolt just keeps the ring in place, basically keeps it from keeps it seated properly in the two pieces of wood. Here's a better kind of color picture. You can see the split of the ring here is like the ring is opened a little bit, so it has some friction as it goes in, because there's going to be kind of a spring force wanting to close it. So it can properly fit in that groove. And then there's a bolt. This is a cutaway, obviously. We would never have it like this. This piece of wood should continue, and then this bolt keeps the two pieces of wood together so that it can engage the split ring. So that's kind of what the tool looks like. So you can drill the hole and make the groove at the same time. And here you can see the cross section where I have the ring in between two pieces of wood, and the ring goes half into one and half into the other. and the bolt holds it together. And you can learn how to design these types of connections in the standard. We're not going to cover it in this course. Another similar kind of connection is called a shear plate. It uses the same kind of idea of having a ring, but in this case, the ring does not go into both pieces of wood simultaneously. Basically, instead of having one ring that's common to both pieces of wood, I'll have one ring that's installed in one piece, a separate ring that's installed in the other, and a bolt that will go through the middle. Now, in this case, the bolt does double duty. It doesn't have to keep the rings in place, but what it does do is it basically, now the bolt is providing the shear. Okay, and what this does is it makes sure that the mechanism for failure is now going to be the shear yielding of the bolt. That's the idea, okay, which is a better ductile shear failure than a lot of the failures that we can get with bolted connections, which involve basically causing splits in the piece of wood and having the bolt be pulled out or crushing the wood, basically. So it's a similar kind of process in that we want to have a tool that cuts the hole for the bolt and also prepares the surface of the wood to accept the shear plate. And so here you can see the shear plate goes right into that piece of wood, and then the surface of that plate is flush then with the piece of wood. Okay, and then I can either do, I can use that to connect steel to the piece of wood, or I could use that kind of connection with two shear plates to join two pieces of wood together. With the split ring, I can only connect two pieces of wood, right? Because the split ring has to be half in one piece of wood and half in the other. So that's not something that I would have any reason to do with steel. But for a shear plate, I can use a shear plate to connect a piece of wood to a piece of steel. So it's basically increasing the strength. It's increasing the strength that can be used with one bolt in a connection, because we're basically preventing that bolt from causing splitting and bearing failures in the wood. So we're more efficiently engaging the strength of that bolt, basically, is what we're doing when we use a shear plate. Okay, timber rivets are a really interesting one. So this is something that was actually invented in Canada, timber rivets in the 60s. And they're like nails, but they have a flat cross-section. So it doesn't have a round circular cross-section like a nail does. It has kind of an elongated cross-section. And the reason for that is it's going to do a better job of getting in between those fibers. So if I have my fibers like this, and I want to put a nail, let's say this is a nail and not a bolt. Okay, I'm just using it because it has a round cross-section. So let's say I have a bolt, let's say I have a nail. The nail has a round cross section, and I put the nail into my fibers. I have to push those fibers quite a bit apart, right? Like I have to separate them pretty far. And some of them are going to get crushed. Like I'm not totally going to be able to separate those fibers apart when I put the nail in. Obviously, always I'm going to damage some fibers when I do this process. But really, the more that I can spread the fibers apart and stick the fastener in between them, the better, because then I get a really high friction in between the two. Okay, so if I use a round one, it's going to be a bit more difficult. If I were to use something flatter, let's say I have a flat, this is just a quarter, let's say I have a flat cross section, then I can fit it more easily in between those fibers, which means I don't have to push those fibers so far apart. But that does mean that if I'm installing timber rivets, which have a cross-section that's kind of flat, I have to install them so that the long part of the cross-section is in the direction of the fibers. If I install it like this, that really defeats the purpose, because now I have to cut through all of those fibers basically in order to fit this in. Okay, so I need to install it so that the flat part is in the same direction as the fibers of the piece of wood. Okay, but then this is a really good way to connect a steel plate to a piece of wood. So it's a simple tool to install them, just like for nails, and very strong. It has a higher load transfer per fastener than nails do, because I'm not so much damaging the surface or damaging the fibers as I install them. So you can see this is a tool used to install these timber rivets. these rivets, you can see a little bit how the head is elongated in one direction. And these ones are lined up with the grain in this piece of material. These ones are lined up with the grain in this piece, and these ones here are lined up with the grain in this piece when they're installed. You know, and this can look very attractive. We have some pieces of steel holding these big diagonal bracing members together, and timber rivets connecting the steel to the wood. And you use a lot of them, and you know, you spread it out over a large area, and you can get a nice high resistance. A lot of teeth. Here you can see a bit better. These timber rivets have the long dimension vertical, and these timber rivets have the long direction of the cross section horizontal. Yeah, so here you can see what that would look like in a schematic form. So the hole in the steel plate will have, the steel plate will still have a round hole, and this head of the timber rivet will kind of wedge into that hole. So it will also keep, it will also reduce kind of the, it'll eliminate the space between the nail and the hole, right? Like if I use a nail in a steel plate and the nail goes through a hole in the steel plate, that hole is going to have to obviously be a bit bigger than the nail. So then the plate can move around a little bit because there's going to be potentially a little gap. So that's not the case with timber rivets, because timber rivet has a wedge that goes into the hole. So as I drive the timber rivet in, it wedges against the side of the hole, which means that the hole can't move. Okay, so timber rivet's kind of like a high performance connector developed quite a long time ago. Something that is really in vogue now is called self-tapping screws. And they're basically screws, but they're really long. And the self-tapping part is that they basically have to drill their own hole as the nail goes in. So these are always kind of a proprietary. There's no standard kind of screwed in self-tapping screw fastener. Depends on which manufacturer you get it from. They tend to be very long like this. They have a really high yield strength, maybe around, you know, 800 MPa, something like that. So we don't typically have to pre-drill when we install these. We have done these in the lab, and we have drilled pilot holes, certainly. For some of the bigger ones, you might have to pre-drill a portion of the depth. So we've run into that before. But you can see all of the different kind of profiles you can get, and you can get them with different kind of heads. You know, this one kind of has a machine bolt head. This one has, you know, like a tapered head. This one has a flat kind of head. And you just install them with a regular drill. I mean, the drill typically has to have a bit more torque than the drill that you have maybe in your basement for fixing drywall and stuff like that. But you can get them in all sorts of sizes. You know, they come up to, you know, 1/2 inch diameter, which is pretty big. I mean, this is 1/2 inch diameter. And they come really long, like you can get them like 1 meter long. And these are really useful for connecting heavy timber members, especially has a lot of application in connections of CLT. So, you know, this has become a very popular choice these days for doing heavy timber connections. I wanted to show you an example from our own work at the university. This is from some research that we did a number of years ago, looking at connecting steel moment yielding connections to timber beams. And one thing that you can do with these self-tapping screws is if you install them on an angle, you can really increase the lateral resistance and stiffness by quite a bit. Because now you're engaging it, not only are you engaging it in shear, but you're engaging it in shear and in tension simultaneously. And these have a really good withdrawal resistance because of the spiral on the shank. So here we had some, you know, we ordered these, and we could order these kind of special washers that allow us to install them at a 45 degree directly. Now, you know, if you sit and think about this connection for a little while, you understand that when I'm pulling on this, it's going to create a tension perpendicular to grain stress in the middle. And so we also looked at, and this came up in a previous live session, for these kind of connections, we installed some additional self-tapping screws. These vertical lines are long self-tapping screws. We installed them vertically throughout the connection to reinforce for tension perpendicular to grain stress. So it's kind of holding the piece of wood together so it avoids splitting. And this all worked very well. So we had this steel connection here. This is a steel yielding W section, like an I-beam. This is meant for high performance buildings where we want to have basically a steel moment frame, but we want the rest of the building to be done in wood. This was our idea. So here you can see my former student installing these self-tapping screws. So there's the special washer. This is like a jig for installing it. And oh, this is the jig for pre-drilling. So he's doing a short pre-drilling hole here in order to make a good angle when he actually puts the screw in. And then you can see here he's using a drill. This is not a very big drill to install the self-tapping screw. And this is what it looks like after it's installed. So here, these are the ones that are waiting to be installed still. Yeah, the only tricky bit was we had to have these slotted holes machined in this plate, which is not such a big deal nowadays because machining these kind of slotted holes and stuff is not so difficult to do with CNC equipment. This is what the final connection looked like. So you can see this basically represents a timber column. This is a timber beam. And in the middle here, we have our yielding section. So this is a steel I-beam that's going to yield in moment. And, you know, I'm not sure if this is the first time, but it might be the first time that maybe someone has designed a connection for wood where we can basically yield the steel. We can totally destroy this pretty big sizable steel connection using wood members to provide the load. So here, the load is applied out here directly to the wood, and the resistance is out here applied directly to the wood. So basically the wood member here is yielding the steel member, and the wood member remains undamaged. That was kind of the goal of our research study. Another type of connection that's becoming popular, and you know, a lot of research has been done on, is called glued-in rods. And this is a connection where you take basically a threaded steel rod, and you drill a kind of large hole in the wood member, and you put the threaded rod into the hole, and you fill all the space here with epoxy, which is a type of glue, and that's why it's called glued-in rods. So we basically, it's not very complicated. You take a rod and you glue it in, and then you make a glued-in rod. And this is just showing the different kind of failure mechanisms that you can have with these glued-in rods. You know, I can have failure of the rod in yielding. I can have failure of the net section of the piece of wood. I can fail in the wood. I can fail in the glue. Or I can get this kind of splitting failure. I mean, this is not terribly important to our discussion here, but here you can see on the right some examples of some ones that we did in the lab, where we installed some rods and refilled it with epoxy, and then we tested these connections. Since there is no current Canadian standard for directly designing these glued-in rod connections, but there are a number that come from Europe, which is what we relied on when doing our design. So here you can see the process. This is for a bigger, you know, these ones were individual ones we just did for test connections. This is one that we did for an actual big structural connection that we were testing, where we wanted to install diagonal steel cross braces in a wood building. And you can see here the process of injecting this epoxy. And this is a two-part epoxy. So basically it comes in two different containers, and you put them all into like this, what's effectively a big caulking gun. And then in the nozzle here, the two chemicals mix. And when they mix, that's when they'll start to set. So we mix the two-part epoxy, we inject it into the holes, and we install the rods. So then we fill it with epoxy, and then we install these rods. You can see the remainder kind of comes out the top. So we try to make sure we get the right amount of epoxy in there, and we try to line them up straight and so on. Here you can see some of my former students doing this. These guys are all, you know, big shots now. This fellow in the back, he's a professor at Queen's University now. These guys are both doing structural design at firms in Toronto and Vancouver. And these are the specimens after we filled in the rods. You can see all these things on top are just to try to keep the rods straight, because we're doing lab research, so we're trying to get them kind of as perfect as possible. And then after that, we had used these rods basically to connect these steel members to the ends of these large pieces of glue lam. So here we have glue lam column, glue lam beam. All the steel plates are connected to those using glued in rods. So you can see like the connection looks very clean and neat. So I don't have to go up the side of this glue lam member at all with a big steel plate, you know, like I did in the screwed connection. So here I have these end glued in rods that are providing the reaction here, and providing this intermediate brace connection where our goal here was to test like an advanced earthquake brace, how we could practically install that into a heavy timber building. So we used some small amounts of steel, select locations in order to do that, and we instrumented all these interfaces to see how those glued in rod connections were faring, which was very, very good. Yeah, actually much better than I even thought. Okay, so those are all of the different types of connections that I just wanted to introduce you to. Going forward, we're going to learn specifically how to design nailed connections and bolted connections, since these are kind of the most common typical connections. You know, glued in rods and self-tapping screws are not really in the design guideline. There are some proprietary methods and stuff to design those types of connections. I mean, it's come a long way, certainly in the past 5-10 years. Even since we did that study, I think it's come quite a long way. But I think that, you know, the idea in this course is if we can understand the failure mechanisms for nails, and we can understand the failure mechanisms for both, those kind of that kind of mechanics understanding is going to transfer well to all the other types of connections that you might run into in practice. So that as long as you understand the mechanics of what's happening in the wood, you can learn how to figure out any type of connection. So that's the end of this video, where we learned how to design all these, or not to design, but we learned about all these different types of connections. And following up this, we're going to talk about different pitfalls that we want to avoid when we're designing connections.